Thanks, Susie, for the invite to update you about FuSuMaTech. First, you could see the new affiliation. This is my first talk after retiring from Oxford Instruments after 31 years. And it's really, I'm retiring from Oxford Instruments, but not from science and innovation. So I started my independent business, Oxford Quantum Solutions. And this is the first talk I'm giving under the new affiliations. For a while, we've been active in the community in advancement of superconducting technologies. And today I'm going to share with you some work which is being started 4 years ago, but is going into its next phase. So to start with, there are diverse applications of superconductivity, and many of you are familiar with these applications. But really, it's only one sector which is really has moved into commercialization and volume production. The rest of the applications are still either demonstrators or prototypes or just attempts to demonstrate the performance of various materials. And in this slide, I'm showing that although the market for superconductive applications exceeding 5-6 billion euros is dominated by MRI, NMR, and the high energy physics and fusion large experiments. And the rest of the applications, so despite so much attempt at moving them from the lab into application, they are still in the lab. And so various leading practitioners were thinking about the challenges why superconductivity hasn't moved into large or volume applications. And the attempt in this program is to look at the needs within Europe for taking the advancement of superconductivity into the next generation of applications. And for obvious reason, CERN and the need for the next generation of experiments in the high field application has led to an initiative led by CEA in Saclay and CERN in Geneva. So Antoine Dalle, who had just retired from CA, was the leading of a working group with and Glenn Kirby from CERN. Together, they looked at the various activities of superconductivity in Europe and visited 11 companies. And they came to the conclusion that there is a need to have an initiative to bring industry and national labs and research institutions together. And hence they started with the FuSuMaTech initiative. FuSuMaTech stands for the Future Superconducting Magnet Technology, and primarily looking at how you can develop the next generation of magnet technologies addressing the needs of the large experiment, but also for commercial applications. So looking for a synergy between industry and how that will impact the future development of products. So there was a call within the European Horizon program on excellence of science, with particular challenge to look at the role of Europe in helping and enhancing the collaboration of research and innovation on superconducting technologies, with expected impact on the role of Europe and the technology and so on. So they submitted the proposal in January 17. It's a single stage proposal with 1.5 million budget and for 18 months. And that was successful in June 2017, and the project started in autumn 2017 for 18 months. It has 4 objectives: moving towards a FuSuMaTech European cluster. So one of the first things the working group has identified is there's a need for a cluster, a consortium of companies working together with the national facilities as well as a research group at a European focus on European expertise. So the second objective was building the FuSuMaTech roadmap. Third one was defining generic R&D actions and also looking at specific pilot actions. So they came out with these four objectives with a primary focus on how to address the needs for R&D for the next class of magnet products, and also try to select a short list of commercial products that will be benefit from the new technologies. These are the 12 partners: CA, CERN, LNCMI, KIT, BSI, and UKRI. These are the national facilities with extensive expertise on superconducting technologies. And the industrial partners were Ansaldo, Billifinger, Elite Energy, Oxford Instrument, Sigma Phi, and Tesla. They sat together and came about with a program which has 7 work packages, some of them admin, some of them about IP and road mapping, policy, and the future of exploitation and dissemination activities. For the next of this talk, I will focus on 2 work packages, R&D and technological pilot programs, work package 4 and 5. So the methodology of FuSuMaTech initiative is to how to link the interest of the academia and research and national facility in the blue, and the industrial, mainly MRI, NMR, and driven R&D, and look at the area, overlapping areas. You can see in the middle here in the green areas, which is relevant for the national programs, but also relevant for industrial players. And they came about, they developed 5 activities in the R&D, which is important for every partner. And they looked at demonstrators to demonstrate these generic. And this is based on the partners coming out with proposals. So these partners came out proposals on magnesium diboride, a 16 Tesla concept magnet for MRI. So everyone knows about the 11 Tesla just being commissioned in CA, but now already people are thinking about 16 Tesla. A social magnet, which is a beautiful idea. It shows what superconductivity can do. HTS inserts for high field. The quest for high field is at different levels, and of course, a gradient technology for MRI. The generic activities, which is relevant for all of them, is quench analysis and modeling, material database, smart diagnostics, helium-free systems, and the high-stress materials. So all these are important for the next generation of magnet products. And I will give you a brief update what these partners has done on each one of them. So in work package 4, which is the generic R&D, it was primarily focused to develop proposals for a pilot project under work package 4 to address the generic R&D. There were 5 tasks on the transient effects modeling of superconducting applications, led by Bernard Ockman at PSI, with support from Elite and KIT. Task 2 was on material property database for at cryogenic temperature. This is so many partners identified the need for a controlled and supported material database, led by Simon Camphor at here Rutherford in Oxfordshire, with support from CERN, KIT, and Oxford Instrument and PSI. Task 4.3 in smart diagnostics, called wireless instrumentation and embedded intelligence for quench detection and management. This is so much is in need nowadays to understand more the behavior of coils in cryogenic environment. It's highlighting how critical it is to understand the quench behavior of system, not just after the quench, but also before it quenches. And this was led by Daniel Colkin at CERN with participation from CEA and Oxford. CEA also led another program on heat extraction and helium-free cryogenics with support from Babcock, Knoll, and Elite. And T4.4 is a new high-stress materials at cryogenic temperatures, led by Klaus Peter Weiss at the KIT with participation from Oxford and CERN. And you could see all of these are really relevant for current problems, but also for future problems. For example, on the high stress materials, if you think about CERN future program on high field, high energy colliders, you need definitely the materials we have now will not stand the high stresses. And that's very critical element. All the fusion programs people are trying to attempt and going into compact system with high temperature don't have the materials which is required. So this just shows how critical it is to start to think in a sort of a structured way about the potential future needs of new applications. So I will start to give a little bit of information about these work packages as presented by the individual project leaders. The deliverables were development plan for generic R&D, test facility, IP management, and the budget and resources for each work package. So in 4.1, on the transient effects, a program of modeling has been developed, started by looking at a survey of what people are currently using, quite very useful to understand what's currently people are using, and then come out with a proposal to address the needs based on the individual users. So looking at the current motivation, future superconducting systems are complex. R&D in technology requires radically new, improved transient modeling, and superconducting applications are niche to be covered by commercial modeling tools like ANSYS or COMSOL and so on. So the team come out with a proposal, and before doing that, they done a survey which has highlighted some of the challenges in terms of material database, in terms of computing power and modeling and simulation, in terms of fast, high performance computing. And of course, validation. When you do a new program, you have to have a validation program which will address the accuracy and integrating diagnostics as well into the modeling. So this program is being split into stages. In stage one, will require about over 3 million euros for 3 years. And at the time, CERN and KIT and TU Darmstadt indicated their interest in that program. And this will be linked to other activities in 5.4, 4.2, and 4.4. Just to show that there is the team come out with a proposal how to address the future needs for modeling and predicting quench behavior and transients. The material database linked to so many of these work packages, again, led by Simon at the STFC, came out with a very advanced program to collate, validate, and provide a generic material database with the capability for individual partners to have their own private database, but still using the same assumptions and allow for sort of a controlled and verified access for various parties. Again, they came with a program and come out with a proposal for delivering within the first phase a 3-year program to provide verified and existing data, testing facilities for low and high field magnet systems, and of course cryogen-free systems with electronic access and maintenance. And the estimated cost for that program was about €4 million. The third one was on smart wireless diagnostics for superconducting cryogenic, again led by CERN, Daniel at Colgan. And again, it's just the first attempt to look at wireless and intelligent measurements and instrumentation to allow some data processing and interrogation inside the cryostat. This is again a 4-year program with just under €5 million, with identifying the material, manpower, and the deliverables based on this program. And this is again something which is various parties showed interest in really having it available. It will focus on superconducting magnet large-scale MRI research accelerators and colliders. It will include superconducting links like electrical distribution, generators, quantum computers, low-cost aerospace devices, and intelligent transport. The fourth project about a novel cryogenic solution for next generation of superconducting application, led by CA, Bernard Baudet, and again develop an experimental program to study and characterize pulsating high heat pipe, which is being developed at CA, develop a specific prototype for different application, and allow a predictive numerical code for designing and implementing a BHP cooling system in real cryogenic magnetic system. Again, the program will have a significant impact on HTS applications, on systems cooled by helium at 4 Kelvin, nitrogen radiation thermal shields, and portable cooling systems. So how you can fast cool systems very quickly. The cost of this program is just under 3 million, spread over 2 phases. First phase 3 years and the second phase 4 years. The final work package, final task in work package 4 was on new high stress materials for next generation superconducting application, led by Klaus at KIT. And again, looking at how some of the large scale magnets or compact system will benefit from new materials, mainly conducting like non-conducting like stainless steel and aluminum and so on. Here showing how the fracture toughness factor function of the yield strengths, and showing that many of the magnet requirements exceeding what's available at the moment. This program will address a new material class, looking at normative guidelines to have established to allow the benchmarking of material production and standardizing of materials. The program will be extending over 5 years with just under 3.5 million euro. So in summary, proposal for the shortlisted generic have been investigated and completed. There are clear benefits for a variety of superconducting applications from the shortlisted projects, and it has identified the need that the generic R&D and the pilot program should be linked strongly together. The average cost of each proposal is about 3 to 5 million, and the total expected cost of the 5 program was 17, just under 20 million euro. And the idea was to go to the European committee and ask for funding for that amount. So that's where this is all starting. Try to get the cluster of partners to go and say these activities has to be done not as an individual but as part of a program. The next work package was work package 5 and focusing on specific applications. So there were 5 of them. Magnesium dipole technology pilot for a 5 Tesla led by Sigma Phi and CA and Ansaldo. A new high-field MRI system up to 16 Tesla led by CA but interested from Tesla, Ansaldo, and CERN. Project 3, social magnet. This is the one which is really I'm finding very attractive myself. Open MRI magnet, MAMO magnet, which is led by Elite, CA, and CERN. And this is really a futuristic project, but it shows what superconductivity can make, the impact of superconductivity on so much of these future needs of our societies. HTS insert for high field is between Bilfinger, LNCMI, and CA, looking at inserts, HTS insert for the national labs in Europe, and gradient coil technology for high field MRI, led by Tesla. So each party have looked at it. So CA and Sigma Phi done a 5 Tesla magnesium diboride system magnet just for testing. And they came about with a program how to take these material into using magnesium diboride for below 5 Tesla and about at around 10 Kelvin. The second one was on the high field MRI going to 16 Tesla, and the benefit, I mean, this is enormous, and there's a need to go to between 14 to 20 Tesla. And there are many, and there's a group in the US working on that as well. And they came about with a program which they think it will advance high field systems in a regime is not available now. The second project was on high field MRI system. Third one was on the open MRI. This is the one which is really looking for a new ways of imaging, imaging, MRI imaging, different from what we have nowadays. So this is the example of currently having 3 people sitting and interacting and talking and really understand what their brain, how they brain. So when they laugh or they talk or they communicate, how the brain works. This is again coming from the system. I'm looking forward to see that in action myself. And you can see the sort of new step change in research understanding of the human brain from such experiment. This is the HTS insert for Saclay. They already have a program, and currently there are 2 further programs from Europe following that activity to understand how to develop the next generation of high field systems in Europe. The last one on gradients, again, I'm looking for gradients for above 10 Tesla, which is completely a new challenge for MRI systems. So all these 5 programs came about with a total cost, again, under 18 million. And these are just to demonstrate these systems. To follow up on securing funding for these 10 projects and also proposing new ideas so that the partners can get some further funding from the EU to follow up on these activities. The conclusion is that to fast track and allow for these new innovation, serious funding has to be provided by funding agencies and directly feeding into developing new products or new capabilities within the European community. To that effect, phase 2 has started, and the next council meeting will be in 21st of April. Existing members and the new members are invited to present where they are in these programs, and to seek new partners and to look for further ideas, and that will be followed by approaching the EU again to see if they can provide a pot of money, say, to address all these projects. So I thought today I gave you an idea where we are and what we are going next. And if you have any ideas if you want to join this initiative in Europe, and you would like to join either as a leading of a project or as a partner, send me some information, and we will arrange for you to join the next meeting. And that's just really a brief summary where we are.
Thank you very much, Ziad.